Swayam Prabha. Digital India. Educated India.
We continue with our discussions on thermodynamics and chemistry of high temperature gases. In this lecture, we will start discussing about the Gibbs free energy, and we will try to derive the condition for chemical equilibrium in terms of the Gibbs free energy, and also initiate a discussion on the equilibrium constant. So, we are going to introduce the thermodynamic variable G, which is known as the Gibbs free energy. So, please take note of this name, which is very, very important. And it is of course expressed per mole of the reacting gas mixture, and we are not at this point committing whether the reactions are happening at chemical equilibrium or non-equilibrium conditions. How is the function G defined? It is defined as H minus Ts, and since H, Ts individually are all thermodynamic state variables, and G is basically a combination of these state variables. Therefore, G by itself is also a state variable. If we differentiate the above expression, a differential form of that would be expressed like this, and on rearrangement in terms of the differential change of enthalpy, you can write it down in the following form. Now, we invoke both the first law as well as the second, and let us see how we can derive an expression based on the combined first and second law inputs. So, from the first law side, you have an expression for del q. From the second law side, you have an expression for ds, and thereby you have a form for ds expressed like this, where the del q by T over here is basically represented in terms of the del q expression coming from the first law. So, this is a combined form. Now, if we multiply all the terms by T, what we end up getting is a form like this, and then what we do is substitute the dH part of this expression from what we had derived in the previous slide. So, we try to use this relation in terms of the Gibbs function. If you do that, then you find that these two terms would cancel out, and you will be left with a differential form of G. Take note of this equation. From this point, we try to take it forward, and before we move on, we try to understand that G can be expressed in terms of say two independent thermodynamic properties P and T if it is an equilibrium mixture. However, when we consider a non-equilibrium mixture, it cannot be expressed functionally anymore like that. You cannot confine it to only P and T or any other two independent thermodynamic variables, but rather it also becomes a function of the number of particles of the species I per mole of mixture, where there are n number of such species. So, this is basically some kind of a population distribution, if you want to call it that way, and it is an instantaneous one. Each one of these can be a function of time, and in a chemical non-equilibrium situation, the instantaneous value of G has to be based on their instantaneous population distribution as well as say P and T. Now, those numbers n1, n2 to nn, they do not only depend on P and T, but also the time history of the process that the mixture would undergo as the reactions progress. Therefore, the total differential of G could be found out if you apply the chain rule using this functional form. So, dG would therefore depend on the partial derivative of G with respect to pressure evaluated at constant temperature multiplied by dP, partial derivative with respect to temperature at constant pressure multiplied by dt, and then a sum of n number of terms, small n number of terms, where you take a partial derivative of the Gibbs function with respect to the population of a particular species I multiplied by dni and summed over all these species. Now, if you take this functional form, then comparing individual terms of the two expressions derived for dG, we will get the following. So, we will just try to go back to the two forms that we are talking about. So, one form of course is what you see over here, the other form is what we left behind, and for that you have to go back to this. And therefore, you will find that this is how, in terms of the comparison, we infer the equality of the corresponding terms in the expression for dG. So, the change in entropy of the reacting gas mixture caused by the irreversible effect of non-equilibrium chemical reactions is what is contributed from this very important term over here. So, if we have a non-zero contribution coming from that summation on the right hand side, then inevitably there is irreversibility addition by virtue of the non-equilibrium chemical reactions, which we were talking about even in the previous lecture, towards the end of the previous lecture. Now, to take the analysis forward, let the small g I dash be Gibbs free energy of species I per particle. So, we are moving to a per particle basis. Let there be Ni number of particles of species I per mole of the mixture. Obviously, if you sum them all, then they would give you the Avogadro's number, since you are dealing with 1 mole of mixture, and since 1 mole contains Avogadro's number of gas particles. Now, based on the above definitions, we can write the Gibbs free energy per mole of the mixture in terms of the small g I dash that we just introduced and the number of particles of species I. So, it is basically a product of Ni times g I dash summed over all the species. So, it is basically an expression for Gibbs free energy caused by species I per mole of the mixture that we are talking about, and that we are going to integrate using the capital G. So, if you expand, it basically looks like this. Each one of the species are contributing to the mixture Gibbs free energy. Keeping track of this equation, if you try to take it forward from that point, obviously dG, when it is when you take a partial derivative of G with respect to Ni, you get back g I dash, the small g I dash, and if you are to substitute that in the T ds irreversible equation, then that ends up giving you a form like this. So, keep track of this equation, keep track of this fact, and that is what we make use of in this equation. So, we are basically talking about this term. We are again revisiting this term, which we earlier mentioned is very important for us to quantify the entropy change due to irreversible effect of non-equilibrium chemical reactions, and we are trying to quantify that. And how are we trying to quantify that? We are trying to work out what del G del Ni represents. From there we can quantify that, and we have come to this point now. Introducing the Avogadro's number in the above equation, we can get a form like this. So, the ds irreversible is now expressed as minus 1 by T, then summation over I species N A times G I dash into d N I by N A. Now, N A times G I dash is nothing but G I. What is G I? It is the Gibbs free energy of species I per mole of I. Now, it is of course different from Ni times Gi dash, by the way, which is the Gibbs free energy of species I per mole of the mixture. So, that is what we had utilized in each one of these terms of the equation for G. And when you look at this term, which figures here, what are we talking about? We are talking about change in the number of moles of I. That is basically what it represents. Now, Ni by Na, it gives the molar ratio of species I in terms of the number of particles. You have to be a little comfortable handling these different forms, which will come with a little bit of practice, but I am sure you will become quite at home with it once you have gone through this material and have practiced a little bit. Finally, if we put all that together, it simplifies to a form like this. So, ds irreversible is minus 1 by T times the summation of Gi times dNi, Ni in script form or italic form. And we need to understand that as we are talking about a non-equilibrium process possibly, which is adding the irreversibility, the chemical reactions progress in such a manner that all the time this summation yields a non-zero value. It becomes 0 once you reach the state of chemical equilibrium, and therefore, the reactions must be progressing in such a manner that this summation always remains non-zero as long as chemical non-equilibrium exists. And as far as the entropy production is concerned, it is purely due to chemical non-equilibrium, and we are not to mix it up, we should not be mixing it up from other sources of irreversibilities which can also change or augment the entropy. So, this has to be kept aside from that. Now, from this we can infer that when chemical reactions are progressing under chemical equilibrium conditions, then how will things happen? It is basically going to work like this, that this summation will go to 0. So, when the summation is 0, then we can say that this establishes the condition for equilibrium chemically reacting gas mixture in terms of Gibbs free energy. This is a very important relation, because we have now made use of the Gibbs free energy in order to define a condition under which the chemical reactions are going to progress under equilibrium. Let us try to obtain the equilibrium constant and gradually apply it for obtaining the composition of equilibrium chemically reacting gas mixtures. We will try to address that as far as possible in this lecture and follow it up with discussions in the subsequent lecture. Now, we recall from our previous studies on thermodynamics that equilibrium thermodynamic systems are always characterized by the fact that thermodynamic state variable is a function of any two other state variables. This is familiar to all of us from classical thermodynamics. This is of course a very, very important principle of classical equilibrium thermodynamics, and when it is a equilibrium chemically reacting gas, then we have a gas mixture. The chemical composition of the gas mixture is also a function of any two state variables. So, we talk about different parameters which can help us define the contents of the different species in the gas mixture. So, it may be the number of particles, for example. So, that is dependent on two state variables. For example, here we have defined the number of particles as a function of T and P. We have also defined the mole fraction capital Xi as a function of T and P, though the functional representations are definitely separate for each parameter that you are talking about. Now, how will all that help us? We will see in due course, but before we take our discussions forward in that direction and discuss more about the equilibrium constant, let us take a slight detour to appreciate the fact that when we are talking about high temperatures existing in air, then how does air respond to that? And we already know from our previous experience that such high temperatures are likely to occur because of the very high speed flows which are moving past the aerodynamic surfaces, for example. So, when we are talking about temperatures like 0 Kelvin, they are far away, much lower than our normal temperatures, and obviously the gas particles are much less energetic in that state and no chemical reactions occur. Until unless you take them to a temperature of 800 Kelvin or so, nothing significantly starts happening. At 800 and onwards, vibrational excitation sets into the molecules, let us say nitrogen molecule, oxygen molecule and so on. It does not affect atoms. However, atoms at that point are not existing because dissociation of molecules can only lead to atom formation, and that starts with oxygen at around 2000 to 2500 Kelvin, where molecular oxygen turns to atomic oxygen. This goes on till about 4000 Kelvin or so, when oxygen dissociation is more or less complete, followed by starting of nitrogen molecule dissociation, which continues till as high as 9000 Kelvin, and beyond 9000 Kelvin nitrogen is nearly completely dissociated and ionization begins, which basically means nitrogen and oxygen atoms then start forming ions and releasing free electrons. So, we are basically talking about a plasma formation, and the range of ionization basically starts from 9000. So, there is a dissociation range, there is an ionization range, there is a vibrational excitation range, and all this is happening with the air at 1 atm pressure. If you are going to alter the pressure, then these temperature ranges are going to get altered. So, the temperature ranges for vibrational excitation, dissociation of molecules to atoms, ionization of atoms and formation of plasma, the temperature ranges that you see over here are very important, but always keep in mind that they are relevant only if you are setting the pressure to 1 atm. Now, it is to be noted that the only exception which does not respond to pressure change is basically the vibrational excitation, while if you are talking about changing the pressure, all other chemical reactions that we talked about would get altered. If the air pressure is lowered below 1 atm, the onset temperatures would decrease. Conversely, if air pressure is increased, the onset temperatures would increase, which means distinctly that they are functions of both pressure and temperature. And we wanted to establish this before we proceeded with our discussions, because you saw earlier that we represented H, E, N, Ni, Xi, etc., all as functions of temperature and pressure, and this behavior of high temperature air makes it more obvious that why we do talk about such pressure and temperature dependencies. In a chemically reacting gas mixture, the equilibrium composition is also given by P and T. In order to find the equilibrium chemical composition of the mixture, we will need to use the relation sigma Gi dNi equal to 0, which we have already derived and shown. Now, to formulate the problem further, just the sigma Gi dNi may not be very convenient enough for us to proceed with. We actually would need to look at the chemical reactions and represent them generically, so that we are able to get closer to implementing that condition for chemical equilibrium by coupling it through inputs coming from the chemical reactions. So, if we write down a chemical reaction generically like this, where all the nu I dashes are basically the stoichiometric mole numbers, and they are there both for the reactants and products. All the ones which are on the left hand side are of course reactants, while the ones on the right hand side are the products, and there are L number of them. While the AIs are the chemical species, the reactants are again shown on the left, while the products are on the right. So, depending on the kind of reaction, chemical reaction, all these species and the corresponding stoichiometric mole numbers would be decided, and the final intention would be to replace the dNi term, which is in terms of moles, by the stoichiometric mole numbers of the reactants and products coming from a generic chemical reaction of this form. That is the way we can couple the things closely with the chemical reactions. Now, we take the reactants to the right hand side and write the generic chemical equation in a form like what we have done over here. So, what you can understand is, in this form, the nu i's with the dashes are now replaced by nu I alone. However, the nu i's are now going to become negative for all the reactants, because they have been taken to the other side, while they will remain positive for all the products. And also see that the dashes are now gone. If you look at a chemical reaction as an example, say we were talking about dissociation of the oxygen molecule producing atomic oxygen. If you look at that reaction, then you find that this kind of a reaction can be represented like this, where this is a 0 and this is the atomic oxygen. They should not be confused, because they almost look identical here, but once you get them into a form like this, you can very well understand that there are two species, A1 and A2 respectively, of O2 and O, and the corresponding stoichiometric mole numbers nu 1 and nu 2 are minus half and 1. So, this minus came up because the reactant has moved to the other side. Now, any change in the number of moles of species I, which is indicated by dNi, due to a chemical reaction, must be proportional to nu I, as indicated by the generic chemical equation. And if we want to talk about an example, then when we talk about the oxygen dissociation equation, then let us say a 0.5 mole increase in atomic oxygen is always accompanied by 0.25 mole decrease in molecular oxygen. If you take another number in terms of mole increase in O, correspondingly you will see exactly half of that number in terms of decrease in molecular oxygen. Therefore, we can easily see that the changes in the molar composition are in the ratio of stoichiometric mole numbers. So, for this above equation, for example, you see that the nu 2 is to nu 1 is equal to 1 is to minus half. So, if the equation contains more number of reactants as well as products, the principle will just get extended. So, in general, you would be able to write an equation of this form, where there could be a large number of reactants and products. Like here, it extends from 1 to up to L number of them, and correspondingly you have the stoichiometric mole numbers extending from 1 to L, and they all occur in a ratio form. So, in order to make things simpler, we will introduce a common proportionality constant, and let us say for a differential change of the ni's, we will have a corresponding differential change of that proportionality constant given by d xi, based on the fact that this proportionality constant is given by xi, which is called as the degree of advancement of the chemical reaction. So, as the chemical reactions progress incrementally, there is a degree of advancement of the chemical reaction that we are bringing into picture. It is basically an index that describes the degree to which the reaction has advanced, starting from an initial or a reference state and moving towards a final state. And as it happens, the mole fractions are going to get changed, and those fractions are going to be related in ratio form with the corresponding stoichiometric mole numbers. So, introducing the concept of xi and calling the incremental or differential change of xi in terms of d xi, we therefore have a relation for any one of those reactants or products generically represented in this form, dni is equal to nu I into d xi. And let us say we follow, let us say that we are following a chemical reaction progressing from a reference condition at which xi is equal to 0 and the mole number ni is equal to ni at a certain reference state, to a subsequent condition when the corresponding quantities have changed to xi and ni respectively. So, we are just tracking the reactions to a certain incremental extent, and then you see that this equation can be integrated between those states, and then you find that on integration it basically comes up with a form like this: ni minus ni ref is nothing but nu I times xi. The relation holds good irrespective of whether the chemical reaction is occurring under equilibrium or non-equilibrium, because we have not imposed the equilibrium constraint anyway at this point. The above relations can help us write the condition for chemical equilibrium as follows in terms of nu I and xi, and you notice that we are now gradually moving up a step ahead of the idea of having the equilibrium constraint restricted to dni, but rather we are bringing in important inputs from the chemical reaction, and that percolates into this equation through the stoichiometric mole numbers. Again, remember that this was common to all the species. It was a common term, as we had indicated in this expression here. It was common to all the species. Therefore, it can come out of that summation, and what basically matters then is this particular equation. So, ultimately the outcome comes out to be like this, and this gives us the condition for chemical equilibrium in terms of the Gibbs function and the stoichiometric mole number of the respective species in the gas mixture. Now, we go back to the definition of Gibbs function, and if we were to define it for a species I, then it will show up in this form. Note that all the terms in the equation are written for species I per mole of I, and that is why we are using the uppercase nomenclature. And recall that we had already derived an expression for SI earlier in the previous lecture, which will now be substituted in the above equation, which means that SI comes in here, along with it comes in the SI reference term. So, we will proceed with this discussion in the subsequent lecture. In this lecture, we discussed about basics of thermodynamics and chemistry of high temperature gases. We discussed about Gibbs free energy, and we established the condition of chemical equilibrium in terms of Gibbs free energy. we started the discussion on equilibrium constant. We also looked at the behavior of air over a range of temperatures ranging from standard temperatures to as high as 9000 Kelvin or more, and we see that it is dependent on both pressure and temperature. Thank you.